We're going to take a look at the Project Lead the Way notes for Activity 1.2.3a, which is the Introduction to Electricity. For my students in this class, much of this is going to be a review of things that you learned during your 9th grade physical science class. Some of you have had physics and gone through this there as well. So take down the notes that you need in order to have this information, or know where to readily find it if you need it again later. We're going to look at Ohm's law, talk about the different ways to talk about flow, conventional and electron flow. We're going to apply Kirchhoff's laws, and then we're going to talk about the difference between series and parallel circuits. Electricity is simply broken down to the movement of electrons. It's an invisible force. We can't see it with our eye, but it provides heat, light, sound, and motion. Because there is the motion of the electrons, there is work involved in this. To understand electricity, we have to be able to look at the elements and understand the properties of them. Atoms are the smallest element, the smallest thing that contains all of the properties of that one element. So one single atom of gold is going to have all the properties of gold. An atom has a nucleus. It's the center of the atom. It has the protons and the neutrons. The protons have positive charges, and the neutrons are uncharged or no charge. The atomic number is the number of the protons in the nucleus of the atom, and it is the identifying factor of that atom. So if we look at this atom, how many protons are in this nucleus, and we can count up the red spheres, and we see 1, 2, 3, 4. Electrons are the negatively charged particles, and they're found out in the electron orbitals. They move around the atom, they move around the nucleus of the atom. We can break them down and we can find that there's these valence electrons, and they are the ones in the outermost ring of that atom. We know that there's a pattern to follow going outwards from the center. The number of electrons in the outer shell goes from 2 in the first orbit to 8, 18, 32, 50, 72. You just need to know how to find these if you need to find them later. When you're doing physical science in 9th grade, you probably talked about them in terms of 2, 8, and 8, and that's about where we stopped. But as it goes farther out, it gets more complex. They're always going to fill closest to the nucleus first and then fill outwards from there. The outermost orbit is going to have 8. When we are filling up our valence rings, we want to fill them up to 8, or we want to get them completely empty. So if we look at this one, it has 1 electron in the valence orbit, right there. Is it a conductor or an insulator? It's a conductor because it has that 1 electron. Sulfur has 6. And because it has 6 and it's going towards 8, it's going to be an insulator. It's not going to readily give that electron away. So if we go back, because this one's going to give that electron away and get rid of it to get down to 0, it's going to be a conductor. Because this one is going to take ones in, it's going to be an insulator. When electrons are moving, they tend to knock each other out from one orbit to another. So they come in, bam, hit, send the other one out. And that is the movement we were talking about a little bit ago. When it loses an electron, it seeks another one to fill the vacancy. So if one gets knocked out, the first one will stay, the second one will go. And so if you look at this, you can kind of watch the electron fling through all of them. Do it again. And they transfer that energy across. If we want to compare the conductors to the insulators, the conductors, the electrons easily flow between the atoms. The insulators, they flow difficultly. They don't want to flow. Usually, conductors are going to have 1 to 3 valence electrons, and insulators are going to have 5 to 8 in the outer orbit. Examples of good conductors are silver, copper, gold, and aluminum. Remember, we talked about your phones are full of heavy metals, including gold, because they're good conductors. If we're looking for insulators, we're going to look at things like glass, quartz, and mica, because electricity doesn't move through them. If we look at a pair of pliers, the metal tips are going to be good conductors. The wires in that wiring are going to be good conductors. And the insulators are going to be the insulation on the outside of the wiring and the insulation on the handle of the pliers. Electrical circuits. We're going to have some abbreviations when we're breaking down the formulas for electrical circuits. It's a system of conductors and components forming a complete path for the current to travel. You've been using circuits since you were little. Every time you turn on a light, when you flip that light, you close the circuit and you make that light turn on. When we look at circuits, we're going to look at the voltage, which is the unit is volts, and the abbreviation is a capital V. We're going to look at the current, which is measured in the unit amps, and a capital A. And we're going to look at resistance. The unit is ohms, and for that we use the omega. If we think about current, we can think about it in terms of a tank and a battery. The flow of electrical charge is measured in amperes, and if we watch when we have the faucet switch off, is there any current flow? Well, there's no water coming out over here, so no current flow. When it's on, then there's current flow. So when the switch is open, then there's current flow. Likewise, when a switch is off on a circuit, there's no current flow. When we turn it on, there is current flow. We're going to take a quick look at the two different kinds of current flow. Conventional current assumes that the current flows out the positive side of the battery, through the circuit, and back into the negative side of the battery. This was the way it was thought when it was first established. This is the way it's often done. It's the convention, and so this is often used even though it's known to be incorrect. The correct way, and the way most scientists use, is the electron flow model, which is what actually happens. The negative electrons go through the circuit and come back in the positive side. It doesn't really matter which one you use as long as you're consistently using one. In general, science classes use the electron flow model, and engineering courses and engineers use the conventional current. Since this is an engineering class, we're going to use the conventional current model, which has energy going from the positive to the negative. So now we're going to look at voltage. Voltage is the force or the pressure that causes the current to flow. It's measured in volts. And when the faucet is off, is there pressure at the voltage? Is there pressure at the switch? Yes, there's still pressure pushing against the pipe and the tank and the faucet. So even though it's not open, there's still voltage. When you turn it on, is there pressure? Yes, there's still pressure because it's still pushing through the system. It's just got a relief point, so the pressure loosens up a little bit. So if we look at this diagram, the battery provides the voltage that will push the current through the bulb when the switch is on. Resistance is the opposition of the current flow. We measure that in ohms. So what happens to the flow of the current if a rock gets lodged in the pipe? Drop, 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 get in there. So what's going to happen? Is it going to increase or decrease our flow? Our flow is going to decrease, right? Because there's something clogging up the pipe. So if we look wide, and then we lodge that rock in there, and it narrows down. In a circuit, resistors are the components that create resistance, and that can include things like light bulbs and the wires. And so the wires cause this, because there's some resistance here, the wires cause this to go dim. Why do we have resistors in circuits? And do you think either conventional or electron diagrams are easier to use? Now let's talk about measuring voltage. We need to set the multimeter. So this machine over here is called a multimeter. You'll be using one in class probably right after spring break if you're in my class right now. And we're going to make some simple circuits. We're going to make ours on breadboards using Arduinos and then power supplies. So you're going to have a battery, a switch, a resistor, which will slow down some of the current, and a light, probably an LED. you're going to measure across the component. So you're going to take the 2 pins that are coming out of your multimeter and you're going to measure them across. So this one is set up here to voltage 20 in the DC. And you can measure that across all the different spots and get your numbers. Using a multimeter, we can measure the voltage, the current, or the resistance. So if we set it to the ADC range, and over there, so it's pointed over this way, then the circuit flow must go through the multimeter, so we do it a little bit different. We take out the line and we just run through the multimeter to get the current. And then to get the resistance, we're going to switch it down to the ohms range, down in here. There's the little omega. And this time we're going to measure across the component that we're testing. So from either edge of the switch or either edge of the resistor and the light. You have to take the power off of the circuit to do this. So notice they pulled the battery away. The battery's not even a factor. You're not going to do this while this is powered up. Ohm's law. If we're looking at Ohm's law, you're going to usually see it written down as V equals I times R, where V is the voltage, I is the current, and R is the resistance, measured in volts, amperes, and ohms. You can rearrange it, I equals V over R, or R equals V over I. Sometimes you'll see it written like this. It's a little bit like the magic triangle, where if you cover up the one thing that you want to find, you can see how to multiply or divide. So if we cover up volts, then you can see that volts equals I times R. If we cover up I, you can see that current equals voltage over resistance. So let's take a look at this and try a problem. So take out a piece of scratch paper and a calculator. Pause this while you do it. And let's try a problem. Ohm's law. The flashlight shown uses a 6-volt battery that has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? Well, if we know that V equals I times R, but we know if we look up here that we have volts and we have resistance, and it's asking us how much current, so we're going to cover up the I, and that leaves us V over R. So I equals V over R. That's 6 volts over 150 ohms. Divide that out, we get 0.4 amperes, because an ampere is a volt per ohm. And then we're going to actually convert that to milliamps. So we're going to move the decimal 1, 2, and get it to milliamps. Now let's take a quick look at circuit configurations. There are 2 primary circuit configurations. The series circuit, where things go through one and then through the next and then through the next and then through the next. And then there's the parallel circuit, where the energy starts out and it splits up, goes through different paths, and then comes back together. Kirchhoff's law, Kirchhoff's voltage law, and Kirchhoff's current law. On the Project Lead the Way test at the end of the year, you're going to need to know both of these, and these are going to come in handy when you're doing the problems. The sum of all the voltage drops in a series of circuits equals the total applied voltage, and the total current in a parallel circuit equals the sum of the individual branch currents. So let's take a look. A circuit that contains only one path for current flow is a series circuit. If the path is open anywhere on the circuit stops flowing to all components. So if we pull out that light bulb and just leave a gap, everything goes out. The old-fashioned holiday lights, this was the case. If you lost one light bulb, all of your lights went out. In the case of a creation my mom had made it as a child, we would spend hours trying to figure out which light bulb was burned out, because burned out would break that circuit. So let's take a look at these and how they work actually as we go through. If we look at the characteristics of a series circuit, then we know that the current flowing through every series component is equal. and the total resistance is equal to the sum of all the